Hi, today we're going to look at something called a two proportion z-test. And it's analogous to the two sample t-test, but we're going to be comparing two proportions from two different groups. So let's take a look at this problem. There's this group of people that have been asked the question, would you marry a person from a lower social class than your own? And of the 421 people who were never married, college students who were asked, 213 were men and 143 of the men said yes. So what you can do there, if you wanted to, is you can calculate your first sample proportion. You can say that p hat for the men is 143 out of 213. And so we just take a minute and divide that. Let me tell you what that is. 143 divided by 213. We get 0.671. Now, among the 208 women, 117 said yes. You can calculate a second p hat. Your p hat for the women is 117 divided by 208. So let's divide that and see what we get. 117 divided by 208, we get around 0.56. So the question it's asking, is there evidence to suggest that the proportion of men who were yes was significantly different from the proportion of women that said yes, and give appropriate statistical evidence. So let me tell you what's not appropriate statistical evidence. If you stopped right now and said, I think 67% is much different from 56%, or much bigger in this case, then, and I think therefore, just because I think it's better, that would not be enough to satisfy what's known as a two proportion z-test. So you'd want to do a little more work than that. So that's where we're going to go next. We're going to talk about how to write one of these out. So the way they always start is you want to start by defining your population parameters. You want to start by saying let P sub m be the proportion of men in the population that would answer yes to this question. Would they marry someone from a low social class? And then similarly, you're going to say P sub W is going to be the proportion of women in the population that would answer yes. Okay, and so now it's time to actually state our hypotheses. Typically, it's just like we always do. HO indicates there's no difference in the two populations, so we would say that P sub men minus P sub women is equal to 0. And HA is usually what you suspect as a researcher. And in this case, the question is there a significant difference? So there's no direction implied that one's bigger than the other. So we're just going to say that P sub M minus P sub W does not equal 0. So this is sometimes called a two-sided test. It's called two-sided when your HA, your alternate hypothesis, is not equal to. Okay, so second step in any significance test is to write out all your assumptions and conditions. So one, these are both supposed to be SRSs, or randomly selected groups of people. I'm not sure the problem even says there. Oh, it does. Look at that, random sample. So we lucked out. So we're going to say yes to that. Number two, you're supposed to check that the population of all men is greater or equal to 10 times the sample size of men that were interviewed. Okay, well, there were 213 men in total. So this is 10 times 213, or 2130. Well, there's certainly more men than that in college that were never married. And then, because of this, usually we can state a standard deviation. So what you can do here is you can say, well, the standard deviation of p hat sub men would be the square root of p hat sub men times 1 minus p hat sub men over n sub men. Okay, so I could take the time to type in these numbers. I'm not going to because we know this isn't really the standard deviation we're interested in. We're interested in the standard deviation ultimately of this. We want to know what's p hat sub men minus p hat women. And the question is, what will that be? So we'll get to that in a minute. You're supposed to check another population. You have to check that the population of women in college that have never been married is greater than 10 times the sample size of the women that were interviewed, the number of women that were interviewed, which is 10 times 208, which is 2,080, and it's certainly more than 2,080 women in college who aren't married, who've never been married. And again, we would get this standard deviation for women, which would be the square root p hat sub women 1 minus p hat sub women over n sub women. So coming up in a different video will be how you do something called a 2 proportion z interval. But that's not today's subject. Today's a 2 proportion z test. And the standard deviation formula is very special because we're doing the whole test assuming HO is true. So when you're doing a 2 proportion z test, you're assuming HO is true. And because of that, your standard deviation formula looks like this. There's a couple ways to write it, but here's a popular way to write it. Square root of p hat combined 1 minus p hat combined, that's what that little c stands for, times 1 over the number of men plus 1 over the number of women. If you want to write this another way, there's another possible way you can write it. You can write it where this expression gets distributed onto both of these. So you could write the square root of p hat combined 1 minus p hat combined over number of men plus p hat combined 1 minus p hat combined over number of women. Okay, so the question is, why do you do this and what's p hat combined? Well, p hat combined, we'll start with that. P hat combined, I'm going to write as the number of men who said yes plus the number of women who said yes over the total number of men in the sample plus the total number of women in the sample. And the reason we do this is because if we're assuming that the 2 proportions are equal, like HO says. If you look at HO, here it is. Here's your HO and HA. HO is saying that the difference between the proportions is 0. So that's the same thing as saying that these two things, P, the proportion of men who say yes, equals the proportion of women who say yes. Well, if they're equal, then we should be able to take our 2 P hats and combine them into 1 P hat combined. So how do you do that? You write P hat combined equals the number of men who say yes plus the number of women who say yes over the number of men in the sample plus the number of women in the sample. I mean, after all, if these two things we're assuming there's no difference between them, we should be able to combine them into one total proportion. So you get 260 on top, on the bottom, you're going to get that 421. And if we divide them, let's do that. You get 260 divided by 421. We end up getting 0.61. It looks like 0.618 when you round it. So that's going to be our p hat combined. So that's what it turned out to be in this case. It's going to be different in all problems, so 0.618. Of the two formulas, I'm going to use this top one here just because it's a little less writing for me. So I'm going to say that the standard deviation of p hat sub men minus p hat sub women equals the square root of 0.618 times 1 minus that. So 1 minus 0.618 will give you 0.382 over 1 over the number of men in the sample, which if we go back to the question, there was 213 men. And while we're looking at it, there was 208 women. So we need those numbers. So we'll keep that in mind. So we don't lose track of it. So this will be 1 over 213 plus 1 over 208. So we type that in for you and see what we get. So when everything's said and done, you get about 0.047. So that's going to be our standard deviation. Okay, great. Our third assumption, I'll have to keep that number in mind. Our third assumption that we really care about is normality. And in the case of proportions, you check normality by doing the following. You check the number of men in the sample times p hat of the number of men in the sample, and the number of men in the sample times 1 minus p hat of the number of men in the sample. Both of these numbers need to be greater than or equal to 10. And if that's true, then you get normality. So in the case of the number of men, there was 213 times p hat for the men, which was 0.671. You can see it right here. This is 0.671. And that turns out to be, when you know it, 143, which shouldn't surprise you at all. And then if you do the bottom one, you get 213 times 1 minus 0.671. And that's just the other 70 men. Luckily for us, both of these things are greater than or equal to 10, so you can check that off. And now you have to go do the same thing for the women. So n number of women times p hat of the number of women has to be greater than or equal to 10. And the number of women times 1 minus p hat of the number of women also is greater than or equal to 10. So we do our math here, we get 208 times, and just to remind you, we had a p hat here of 0.56. So we're going to put that in here, 0.56. That's from the 117 in the numerator. So if you actually multiply those out, sorry about my screen jumping on you there, this ends up being 117. We do here, we do 208 times 1 minus 0.56. You get the other people. So you get 91. You should notice, for example, like 117 and 91 together give you 208. Up here, you should notice like 143 and the 170 give you 213. That's not a coincidence. So then because of this, we have normality. We can say that the following, because of both of these things, we can say that p hat of the number of men minus p hat of the number of women is approximately normal. Okay, moving right along. So now we can actually start to draw a picture and move on with it. So we draw a normal distribution, which we know is normal. We just proved that. We mark off 0 in the middle because that's our HO. We know our standard deviation is 0.047, so I can mark that above here, 0.047. If I do an extra 0.047 above that, we'll land at 0.094. Go down to negative 0.047 and negative 0.094. And that looks pretty good. And the only thing left to do now is mark off what's our actual difference in proportions. What is p hat sub men minus p hat sub women for this problem? Well, right at the very beginning, one of the first things we did, I'll circle it here for you. Well, let's highlight it even. We found p hat sub men to be 0.67, and we found p hat sub women to be 0.56. So if I go over here and I type that in, this is 0.67 minus 0.56. 0.67 minus 0.56, and we're getting 0.11, which you'll notice is pretty far away. That's out here somewhere. That's where 0.11 is. So our normal distribution will go out pretty far, and we would have a pretty small error out here in this tail. Now keep in mind, HA in this case, HA was that p hat sub, not p hat, forgive me, just P. So it's very important. You don't want to make that mistake. The proportion of men in the population minus the proportion of women in the population who would say yes was not equal to 0. So this is called a two-sided test. So you have to go down to over here. We'll extend this graph a little bit further. It looks like we're going to mark off negative 0.11 and shade below that. Okay, so we're just about done here. We're going to find our z-test statistic. So it's going to be z equals p hat sub men minus p hat sub women minus HO, which is 0, over the standard deviation of p hat sub men minus p hat sub women, which is that crazy formula we worked on. This turned out to be 0.11 on top over 0.047 on the bottom. And if we divide those, we end up getting something a little bigger than 2, I guess. Yeah, it looks like you get around 2.34. So once you've done this, it's time to convert this into an area, which you can use a z-chart or you can use normal CDF on a T84. So what I'd probably do is I would do normal CDF, my lower bound of 0.234, my upper bound of a huge, huge, huge number. And since this is a z-score here, the mean of all z-scores is 0, and the standard deviation of all z-scores is 1. So if we take a minute to calculate that, let's see what we get. Should get something pretty small. If we do, it looks like we're getting around 0.0096. Now, that looks significant, but just be careful. Just make sure you're all right. We got to double that because there's a second tail over here, right? This is a two-sided test. So if we double that, not much happens. It's still pretty small. So we do times 2, and we end up with a p-value of around 0.0192. That's what we get, a p-value of about 0.0192, which is really small. It's less than alpha equals 0.05, right? So our 0.0192, our actual p-value, is certainly less than alpha equals 0.05, which is a popular alpha level. And that would tell us that we would reject HO in favor of HA, and that is letting us know that the proportion of men in the population say yes, I would marry someone of a lower social class, is significantly different or not equal to the proportion of women who would say yes to the same question based on this sample. So there you have it. That's your first two proportion z-test. Thanks for watching.